Hi everyone, thanks for attending my presentation. My name is Sheng Guan. This is a joint work with Peng Lin, who is from Washington State University, Han Chao Ma, and my supervisor Yinghui Wu, who are come from Case Western Reserve University. This work is about how we detect nodes with erroneous information in graphs with an adversarial few-shot learning-based framework. We call it GEDet. Ensuring high-quality data, such as knowledge bases and social networks, is important for various downstream applications. However, high-quality data in the graphs is hard to obtain. Detecting errors has been extensively studied for relational data and has been recently extended to attributed graphs. Erroneous node with incorrect values can be captured as violation of rules, statistical outliers, values that do not conform with an identified pattern. Such a diversity cannot be fully captured by a single model. Meanwhile, it is difficult to obtain a full set of correctly labeled examples, especially over large real graphs. This issue remains in error detection by crowdsourcing due to labels with low quality. Thirdly, there is an issue of inherent incompleteness of real-world graphs. Missing edges leads to the insufficient neighborhood, hence may downgrade the performance of error detection. For example, the constraint-based detection and message parsing-based learning. To sum it up, existing methods are limited to dataset-specific side effects. It is essential that we have a graph error detection model which only needs a few labeled examples. Considering the following example from real-world knowledge graphs, let's assume we have a graph constraint that states if a movie is based on a book, then they should have the same genre value and main subject value. Then the erroneous node V1 can be detected as its genre violates this graph data constraint. Film V1 has a genre said film based on novel should be fantasy. Similarly, if there is another rule state, if a movie is a subsequent of another movie, then they should share the same genre value. In this case, the genre of V2 also need to be fantasy. Secondly, the attribute duration of V2 here can be treated as an outlier. We can clearly see that the union of rule-based detection and outlier detection still cannot capture the error in V3. Since there is a missing link between V2 and V3. Meanwhile, time travel is a common subject that won't be treated as an outlier. Hence, applying individual method or a simple union of their results may not capture all the errors from different scenarios. Detecting multiple types of errors is challenging. In the graph, we naturally could assume we have a small set of erroneous nodes whose correct counterparts are known. These correct counterparts can be given by domain experts. Then our task becomes we would like to detect selected nodes that carry erroneous attributes, but their correct counterparts are unknown. In our approach GEDet, we treat it as a node classification problem. How will we get the training data to tackle with the challenge, lack of examples, In our few-shot error detection module, we apply an error generative model to simulate how different types of errors are generated. To tackle with the challenge inherent incompleteness of real-world graphs, we apply a biased link inference model to enhance the neighborhoods. Then the question becomes, what classifier should we use? We bring in a generative adversarial network that is short as GAN model. In the GAN model, we learns a generator to simulate the distribution of real data in the graphs by forcing the discriminator to differentiate not only error and correct, but also synthetic and real labels. GEDet improves the accuracy of error detection. Now let's take a look at the framework of GEDet. Roughly, we have three major components. First, we call it scope graph, which prepares the initial features for the subsequent machine learning task. Then we have a graph augmentation module to simulate how the error is generated from different scenarios, and to enhance the neighborhood to facilitate graph representation learning. Next, we bring in a graph representation module as graph autoencoder. We feed this representation to the GAN model that further improves the accuracy of error detection. In our first component, the scope graph, we want to derive proper vectorized representation of graphs. In this step, we convert the attribute to a fixed dimensionality of features. For example, we can use multiple layer perceptrons based on different types of nodes to convert the attribute to a fixed size of features. Then, depending on the applications, sometimes if the nodes of our interest are not directly connected, for example, in a citation network, we can define the metapath like paper author paper to connect two entities of nodes. Then in the second module, graph augmentation, firstly, we want to tackle the challenge, lack of examples, and there are multiple different types of errors from different scenarios. We apply an error generative model. In the error generative model, first we learn a set of transformations from the graph data. The transformations can be quite general, such as add, remove, exchange characters. The second step is we want to determine how different transformations should be applied if we observe an attribute. The philosophy is we want to assign the probability for transformations such that after we apply the transformation on the correct counterparts among all the training erroneous nodes, the overall similarity between transformed attributes and observed errors is maximized. In the end, we apply a prioritization strategy to inject errors in selected nodes to balance the number of labeled correct and erroneous nodes. Error generative model simulates the generation of various types of errors. To tackle the second challenge, missing edges, we apply a link inference model here. We applied a biased supervised random walk as the module for neighborhood augmentation. GEDet first samples a set of S as source nodes from training nodes with some heuristic as node importance measurement, such as degrees, betweenness, for each node in the source node S. It assigns a set of positive nodes that either have the same class as the source node or have a higher node similarity with the source node. We call it positive set. Then our goal is, following the transition probability matrix we learned, it is more likely to visit similar nodes with the same class from the source node. After the transition matrix M is learned, we get it by this transition probability matrix, inferring meaningful connections as long-range dependencies to complete the graph. It has been studied and verified in other work that long-range dependencies can contribute to improve the graph representation learning. Then to sum it up, previously in the scope graph module, we prepare the attribute level representation and node level representation. However, we haven't considered the neighborhood of each node. The success of graph neural network suggests that we should leverage the neighborhood information to learn the representation for the downstream error detection task. In the GEDet, after the graph augmentation, in the augmented graph, we choose to use graph autoencoder to learn the graph representations. As the last step, we apply a GAN model as the classifier to detect the errors in the graphs. The GAN model learns a generator to simulate the distribution of real data. The generator minimizes the loss between fake node embeddings and the real counterpart, such that the generator has a higher chance to fool the discriminator. In the discriminator, by forcing the discriminator to differentiate not only error and correct, denoted as supervised loss, but also synthetic and real labels, denoted as unsupervised loss. GEDet improves the decision boundary for error detections. Next, we justify how our adversarial detection module improves the accuracy of error detection. When the generator generates synthetic samples in low-density areas, it will also make the classifier in the discriminator be aware of these low-density areas, which benefits separating the correct and error node clusters. In this way, GEDet improves the decision boundary for error detection. To evaluate GEDet, we use 3 real-world large heterogeneous graphs. Based on the discussion before, we get 8 scope graphs. We implemented a configurable error generator that enhances BART, which is a benchmark tool to introduce erroneous attribute values to real graphs. This error generator injects graph data constraint violation errors and random errors such as outlier. In the competing method, there are 3 main categories. The first category is anomaly detection. We have outlier detect and allied, that is a method considering both the topology and attribute. The second category is constraint-based error detection method. We have GEDet. The third category is ensemble-based approaches. We have some state-of-the-art approaches like Raha and hybrid. To illustrate the effectiveness of proposed modules in the GEDet, we also implement several variants of GEDet. We first have GEDet-C. It is a simpler game-based alternative with no graph autoencoders. In the GEDet-C, we don't leverage the neighborhood information when we learn the graph representation. A second variant, we replaces game-based classifier with a much simpler graph convolutional network-based classifier. The last variant is a graph convolutional network, which is a semi-supervised node classifier. We collect all the results on a giant table. In this table, the bold means best result, the underline means the second best. We define the precision, recall, and F1 score on the arrow class. To illustrate the effectiveness of GEDet framework, we have several takeaways here. First, there is no single winner, especially on precision. If we look at several datasets like agent, music, and transport, the precision of the constraint-based detection is very high, with the sacrifice of a low recall. If we use a relatively balanced metric F1 score, their results are still poor. The second takeaway is GEDet achieves either the top or the second best results in precision, recall, and F1 score in almost all the datasets. The overall performance of GEDet variants are relatively more stable for different node types and errors compared with competing methods. Next, we evaluate the impact of factors to model performance. The first factor is the data imbalance. We can see that the GEDet variants are less sensitive because we have a graph augmentation that can counteract imbalanced training examples. The second factor is training data ratio. As we can observe, the accuracy decreases as less training data is available. However, GEDet is the least sensitive. In the end, we look at a real-world showcase of errors that can be captured by GEDet but are missed by GEDet or outlier detection. We used entries from Wikidata editing history as testing and leverage the logged correction history as ground truth. Because there is a missing link between V1 and V2, the graph constraint-based detection method cannot detect the erroneous node of V2. Similarly, since VW Polo are quite common values, they won't be treated as outliers, so the outlier detection failed to detect the node V2 and V3. GEDet can successfully detect the erroneous nodes under multiple erroneous scenarios. To sum it up, GEDet enables few-shot learning-based error detection framework with a novel graph augmentation strategy. To cope with lack of examples, GEDet enhances supervised information with both synthetic error node and non-local neighbors. The detection module explores the principle of adversarial learning to improve the accuracy of error detection. Thank you, and the code and tools of GEDet are available in the GitHub repository.